Hello, everyone. Welcome to this second state-of-the-art session, Revolutionizing Diagnosis and Discovery with Artificial Intelligence. My name is Fred Howard. I'm a breast medical oncologist from University of Chicago. And this topic was chosen because I think we've seen in this last year and the year prior, this just evolution of artificial intelligence has really percolated through all aspects of our lives. And it's also impacted how breast cancer is treated. So we wanted to give an overview of where we are now and where this field is heading. Let's see if that works. Well, I'll just click. In 2024, we saw a Nobel Prize for Chemistry was awarded to the researchers behind the development of AlphaFold. And in this past year, we've seen the latest models achieve unprecedented levels of accuracy for predicting protein structure that is essential for drug discovery. I think many of us have been impressed by these language models that have been developed, that including those by OpenAI, that can answer PhD-level science questions more accurately than PhD experts. And these same advances have continued to impact cancer care. There's been an exponential rise in the number of FDA-approved devices incorporating artificial intelligence techniques. In breast cancer, these are mainly devices related to radiographic imaging, like for the automated interpretation of screening mammograms, or for the quantification of features on pathology. AI has been applied in other domains within clinical practice, including the drug discovery process. Traditionally, drug discovery can take up to a decade and cost over $2 billion to bring a drug from target to actual practice. And artificial intelligence is being used in all aspects of development, and we're starting to see these drugs enter into clinical trials. So today, we're going to see presentations that help to answer questions such as whether we can go beyond what the human eye can identify from pathology slides to extract additional information indicating prognosis or potential treatments. We're going to see if radiologists will be using artificial intelligence to interpret imaging, or to what extent artificial intelligence could replace radiology. And we'll also see if drugs designed by artificial intelligence can be more effective, less toxic, be used towards novel targets, or if artificial intelligence can be used to identify the right treatments for the right patients, or incorporated in other domains of clinical practice. So with that, I'd like to welcome Dr. Kun-Hsing from Harvard Medical School to talk about applications for pathology.
Thank you very much for the introduction, Dr. Howard. So in this brief session, I would like to talk about some of the recent advances in AI for pathology, especially related to pathology diagnosis and research discovery using AI-based approaches. So first, we will talk about a recent multimodal AI foundation model for predicting multi-omics and survival outcomes using just a standard H&E stand pathology slides. And we will also cover additional clinical applications of this pathology AI model, specifically for breast cancer evaluation. In the last 3 minutes, I would like to talk about some of the ongoing challenges we are still facing in this field and what we can work together to overcome those clinical and technical challenges. So first of all, about the multimodal AI foundation model. So what is a foundation model? A foundation model is a model that is trained with large and diverse data set with lots of parameters in order to capture the essence of the data with the intent of being able to apply it to various different applications. For example, ChatGPT is a foundation model that was trained with Wikipedia and many other data sources collected over the internet. And these days, we can use GPT to edit our manuscript or to plan our itinerary and the like. Similarly, our research goal here is to see if we can develop a pathology-specific foundation model that will further enhance different forms of pathology evaluation. And in this recently published model, we call it Clinical Histopathology Imaging Evaluation Foundation Model, or CHIEF model in short, published a few weeks ago in Nature, where we collected more than 60,000 whole slide images, and that amount to more than 900 million image patches from these high-resolution histopathology slides, spanning 19 anatomical sites. So for our data, we first collected these whole slide images. We tiled them into manageable image patches because of the raw dimension of these whole slide views contain billions of pixels. And after we obtain these tiles, we pipeline into this image encoder to extract machine-readable formats and features. In addition to the image part, we also collected the associated pathology reports, and we use those reports, pipeline into a text encoder, use the OpenAI release CRIP model to align the embeddings or text features with the associated image features. And at the end of the day, we aggregate the signals collected from various views in this image tile into a whole slide-based representation of our sample. And with the extracted features, we can use it to build various downstream tasks. For example, for pathology diagnosis, molecular prediction, or survival outcome prediction, all using the same extracted features. So how does our result look like? Here's a summary of our results on a very important clinical task on detecting cancer cells from whole slide pathology images. And here we show a series of results on the receiver operating characteristic curve. On the y-axis here, we show the sensitivity, and x-axis, we show 1 minus specificity. So the closer to the upper left corner means that the model has better performance. And as we can see from this comparison between different models, our chief model in red has near perfect performance across various types of cancer. For example, in detecting cancer cells from breast cancer, colorectal cancer, and many other cancer types, we have an area under curve of more than 0.98. This shows that our model can reliably identify the regions requiring either additional analysis, or we can more efficiently flag those regions for evaluating pathologies to direct their attention to the regions of interest. And importantly, our model also outperformed comparing with other models by 10 to 15% in terms of overall performance. And our next research question is, can we utilize the same approach to further identify additional hidden information from our large-scale whole slide pathology images? As an analogy, here's a picture simply consists of some random dots and lines. And the question to all of us is, can we identify the hidden signals from this particular image? So if I tell you that the painter who created this image intentionally put an animal and a plant into the image, can we identify them? And it turns out that there's a dog and a tree hiding inside of this image. Similarly, in digital pathology analysis, we routinely encounter billions of pixels in this high-resolution whole slide scan. And the question is, can we identify the hidden signals out of these digital pathology images? For example, can we directly read out genomic alterations from the standard hematoxin and eosin or H&E stand pathology slides? And surprisingly, the short answer is yes. Using our chief foundation model, we successfully predicted the mutation status of clinical importance. On the figure panel on the left, we show the prediction results of many prevalent mutations stratified by cancer types. For example, for breast cancer specifically, listed here, we have been able to predict the mutation status of CDH1 among many other genes with more than 5% prevalence in our training set. And if we focus on the mutations related to FDA-approved targeted therapies, including ESR1 and many others, we have a prediction performance of around 70 to 90% in our area under the curve, showing that our foundation models using AI, we can recognize additional signals not so pronounced by the human evaluation, but those are related to the mutation status, related to treatment responses. And future work could extend this model to further stratify patients into different potential probability of responding to FDA-approved or other emerging treatments. In addition, we further extended our approach to directly predict the overall survival outcomes after the standard treatment. And in this set of survival curves, we stratify them by cancer type and the stage. And on the x-axis, we plot the time after the initial diagnosis in months. And y-axis, we plotted the survival probability. And here we show that we can reliably differentiate those with different mortality risk. For example, in our final model, we divided the patient into two groups, the blue group with lower mortality risk, while the red groups had higher mortality risk, and we show statistically significant difference in these two groups. In terms of the concordance index, shown on the lower right, we also show that our foundation model approach outperformed standard digital pathology AI models by 10 to 15% in the concordance index. And interestingly, we can further look into the regions receiving high attention from our AI-based analysis and try to learn from what are the important signals related to survival outcomes after stratifying for cancer stage and other well-known pathology biomarkers. And here show that for a high-risk patient with breast cancer with high mortality, our model directed its attention into regions with necrotic tissues, as well as regions with infiltrating tumor cells. Whereas for a low-risk patient, our model put a lot of attention into the well-preserved glandular patterns, showing that our model can reliably detect the tumor microenvironments related to overall survival outcomes. And we further extended this approach to build actual clinical applications related to extending these explainable AI methods to reveal additional insights into the prediction of important molecular and clinical outcomes. For example, here we built models that reliably predict the estrogen receptor and progesterone receptor status with accuracy of more than 0.98. And we show that our model directs its attention into the regions with lymphocyte infiltration and identify patterns indicative of such hormonal receptor status, showing that our data-driven approach can reliably identify any hidden signals related to clinically important outcomes or molecular aberrations. So here we have showcased a few potentially useful clinical applications building up on our foundation model and many other AI approaches. And what are some ongoing clinical challenges in implementing such models in clinical settings to augment clinical decision-making? In the interest of time, here I only highlight one crucial challenges in this domain on implementing and further developing such AI system, that is to understand the problem of context using end-to-end AI model. So the problem of context, or in the academic term, is called the frame problem. It's not a new problem at all. It was first described in the literature more than 50 years ago, when previous generation of computer scientists and AI developers tried to develop an end-to-end robotic system to navigate the real world. And they soon realized that it is challenging to identify a set of axioms or assumptions in their words to properly describe the environment for such autonomous agents. So what does this mean? Let's look at the real-world example. So here's an image obtained from the internet. And the question to all of us is, what is this animal? Is it a tiger or a dog? Well, at the first glance, the morphology, if you will, of this particular animal really shares some similarity with that of a tiger. However, if we consider the overall context and other objects within this environment, we will soon realize our initial mistake. And as a human being, we can easily update our prior belief to make a more accurate posterior evaluation. And after identifying our initial mistake, we joke about it. One user on the internet said, "I was convinced, without a shadow of doubt, that was a tiger." Another user said, "With a shadow of doubt, it was a tiger. But without a shadow of doubt, it was a dog." And the third user just say, "Seems shady." However, when I input the same image with a context into the state-of-the-art multimodal AI model this morning, here are the results I got. So our model still believes this particular animal is a tiger without a shadow of doubt. And the relevance to pathology AI is that in pathology AI image analysis, we also routinely encounter this problem of context, and there are various exceptions in pathology that we need to account for. For example, there are many artifacts in our whole slide images, and they are related to laboratory context. In addition, to arrive at the accurate clinical evaluation, we often need to consult clinical correlations to make a more comprehensive evaluation. And for 1% of the slides, after this standard pathology image processing and slide scanning, they will still encounter some slight scanning errors. And those errors will generate additional image artifacts that is not so obvious to end-to-end AI models. And the solutions we develop in our lab is we develop auto-distribution detection methods to at least flag the samples with atypical image manifestations. And multimodal learning, including using large language models to mine the medical literature as well as the clinical records, may be helpful to seek additional clinical correlations. And at the end of the day, perhaps having human in the loop is still important when we have imperfect pathology AI systems for making the final diagnosis. In summary, here we have showed the multi-model foundation AI system that could enable patient diagnosis, molecular profiles, and prognosis using pathology image analysis. And we developed explainable AI systems, specifically focusing on the prediction of ER, PR, and many other clinically important molecular profiles. And it revealed lymphocyte infiltration patterns and many other imaging features related to such molecular alterations. However, multidisciplinary research is still required to further address these technical and implementation challenges. And because of these challenges, with apologies to JFK, perhaps we should ask not what AI can do for you, but instead ask what we can do together to build a better future with AI in medicine. Thank you.
Thank you, Dr. Yu. So we're going to do questions at the end of the session, so hold your questions. Next, I'd like to welcome Dr. Ritse Mann from the Netherlands Cancer Institute, who's going to talk about imaging and screening.
Okay, thank you for having me. Let's see if I get some slides, then we'll get started. Okay, we're going to talk about AI in breast imaging in the whole range that I can think of. I work with a number of companies also on AI studies, so that's quite obvious. Radiology over the years has changed from looking at 4 images roughly to looking at tons and tons and tons of images. That made our work a lot more cumbersome. We needed a lot more radiologists, but still the number of radiologists compared to the number of images is going like this, right? So we need to somehow change our efforts a little bit, and many of these images are quite similar. The tasks that we perform are repetitive, so the idea is, can we ask the computer to do that for us? I'll take you to some of the very basics just to run over the alphabet soup. This was supposed to be CAD, computer-aided diagnosis as it was called. And this was developed in the 90s. It found then things that we would easily miss, like microcalcifications here, and it would place a black angle on top of it that was very annoying because due to the black triangle, you did not see the calcifications anymore. Anyway, you got sort of the gist of what this can do. AI, as it's now, is also CAD, right? There's a big circle here that says artificial intelligence, and that includes all kinds of machine learning and computer things. It even includes robotics. Within that is machine learning. That's mostly the old CAD. Within that, we'll find neural networks and then deep learning. And within the deep learning, we find the convolutional neural networks. They are around since 2012, 2014, more or less. That is what we currently call AI, right? But it's all just an iteration of the previous process. Machine learning here, deep learning there, convolutional neural networks there, and now we're talking mostly about transformers, diffusion networks, and so on. The paradigm shift in AI compared to CAD is basically this. Originally, we told the computer, look for a star, and if you see a star, it's a yes. If you find a circle with a clear margin, then it's a no, right? We're talking malignant benign differentiation here. Nowadays, what we do is we dump in a lot of yeses, we dump in a lot of no's, and we ask the computer, this is a shape we've never seen before, but can you tell us whether it's more yes or no? And eventually, it actually does tell us that. Remember that what we do in medical imaging is applying models to data. This is a very classic deep learning model called the UNet. It actually is very good in segmenting the lesions, and therefore is more or less the current standard, but there are newer ones out there already. We do not develop the AI algorithms within our playing ground. We actually use that from the mathematicians that develop these things, and we just put the pieces together and then actually train a network to actually get us a better outcome. Prerequisites, very clearly, you need loads and loads of data. This is a very classic example from self-driving cars, right? One of these ladies will not actually to the other side of the crossroad due to the simple fact that this lady here is walking with black shoes. If you have enough data, then you will learn quite rapidly that whether the color of the shoe is red or black or green or whatever doesn't really matter. You still stop. CAT mammography has been around and developed in the 90s. It was approved by the FDA in 1998. And then early 2000, everyone was very happy with it, also because it was actually reimbursed, I think. I think here in the States, roughly 85% of hospitals are actually using CAT in their daily practice. And this number is still going up. However, already in the late 2000s, people were asking, is this really useful? And in 2016, this study was published that sort of said, well, maybe better not. They compared centers that used classic CAT for mammography screening to centers that did not. The black RC curve is the one from the centers that did not. The red one is the one from the centers that did. Consequently, using CAT decreases performance. Not so strange, because this is what we call automation bias, right? If you use a lot of CAT or AI, whatever you want to use, you sort of tune yourself to the AI, and in general, you tend to follow more and more. That's not a big issue if the AI is really better than you are, but if it's not, you get these kind of results. So it's a little bit of a tricky thing. Nonetheless, same year, this man, Geoff Hinton, told us that we should stop training radiologists due to the simple fact that AI would actually replace us within 5 years. We are 8 years past, so we have survived that wave, but this actually means something. This is not a nobody. He actually got a Nobel Prize this year, right? And that means our job is definitely changing. What does the current AI do in radiology? Well, a lot. It can do all these different things. And just to focus on a couple of them, image generation and tissue segmentation. These are MR images. Strange MR images, you will not put a plane in an MR. But what the scanner actually generates is here, the top row. This is called case space. And the center image is the one that actually is the full image. In the center of case space, on the left side, you'll find the contrast. You'll find the high resolution lines, so the boundaries, in the periphery of case space. Obviously, what we normally do in an MR is not acquiring the full case space. Rather, what we acquire is something like this, about 1/8 of the whole case space. And then we fill the image with zeros and then actually get an image, because that goes way quicker, right? You obviously see that if you fill it only with zeros, it doesn't go well. So we have computational methods to actually optimize the image quality, and they are like the compressed sensing here. Right? It takes roughly 15 minutes for a computer to calculate that, but you can also train an AI algorithm to do it for you. And then in milliseconds, really in milliseconds, you get this image that's even better, because the AI algorithm knows what the image should look like. This is in the hood of our scanners. This is in the images that you're looking at. No one is telling you that that is the AI, right? But it's already there. You actually use it even further and create missing data. In MR, we acquire multiple different sequences, T1, T2, and so on. And you can actually use the redundant data in one sequence to generate the other without actually scanning it. Especially things like T2, but also native T1 without contrast are very easily generated from the post-contrast acquisitions. What you can potentially do is create images like this, where we have combined a diffusion image with a T1 pre-contrast image, so there's no contrast in this image, and there is still contrast in that image. They look quite the same, but this is actually diffusion, right? And this is contrast, just to make our lives easier and actually try to spare contrast. We aren't there yet, right? But eventually this might actually happen. Then we do things like tissue segmentation. How big is a lesion? Where do you find it? What are the actual sizes? And there are algorithms out there like Segment Anything, where you just draw a bounding box around an organ, let's say the liver or the kidney or a spleen, and it will automatically segment for you that organ due to the simple fact that it knows where the boundaries are of these type of tissues. Sometimes you also don't see that is happening. This image here in the middle is what's called a smart MINIP, and it's smart because it's generated from a 3D ultrasound breast image. That actually is a wide scanner that goes over the breast from the top to the bottom. And in the back, it always scans part of the lung and the ribs. The lung and the ribs in the back are black. Right? So if you would have a real minimum intensity projection, what a MINIP is, then it would be completely black, because the last image is basically black. So there's actually already a segmentation in this image that just cuts away the chest wall and only projects the breast for you. Once again, no one will tell you that's there. And AI can sometimes make small errors, just to be aware of these kind of things. Then the more important parts, right, more common parts, lesion detection, for example. This was the first CNN that we let run on mammographies. And as you can see, we actually put in patches due to the simple fact that at that point in time, our computers could not handle more than an image patch. Nowadays, we send a full stack of tomo through it, 60 full memos per view, right? And it just runs that in a minute or so. That is 8 years, right? You also see how fast it's actually developing. Currently, AIs for lesion detection in mammography and also, I think, in tomosynthesis are better than radiologists, especially in reader studies like this one from the Korean group, this one from Britain, where you see that this is the first reader, that's the second reader, this is the performance of the AI. 2 readers in consensus here are still better, but you see these curves actually crawl towards the consensus read of 2 radiologists. This is from a British testing system. It's called Performs. If you screen mammograms in Britain, then basically you need to practice every year 60 cases or so. So these same cases have been read by 525 radiologists and by one AI system that performed at the 88th percentile of these readings. So you see how good they actually are. In reader studies, AI completely outperforms humans. In regular practice, it's actually a little bit less. More or less performance is the same due to the simple fact that radiologists in reader studies, I also think pathologists, do perform worse than in their everyday job. In prostate cancer, you see exactly the same. In reader studies, AI really outperforms the radiologist. In real practice, it's more or less the same. It's like lung are catching up, right? They are not yet at that level, but we are getting there. Obviously, AIs sometimes make unfortunate mistakes. Be aware of that. I don't think there's a single breast radiologist who missed this cancer, but I think the AI thought there was a cyst. Also, for things like recurrence detection, where there are already abnormalities in the breast, somehow reduce a little bit the performance of the AI system. The question is, can we use this great performance of AI in general to our advantage? The standard thing is to use AI next to a radiologist, right? You have a radiologist reads with and without AI, and then actually you see that there is a little bit of an increase in the ROC curve. Very nice, but not very useful. Most of the time you're either here, you know there's cancer, or you're there, you know there's not, and there's not that much benefit. Nonetheless, I think that with the LMs that are currently out there, the language models, the output of a mammography machine will change from this to this, right? It will segment the lesion for you. It will tell you what you look like. And I think only this box will be empty. And eventually you just hit a 5 and say, okay, this is cancer. What you can see is that AI can also assign risks to mammograms. In this case, normal mammograms are distributed in equal batches of 10%, with the highest risk, obviously, in the 10. The cancer distribution is quite different, right? Most of the cancers are actually in the 10. And you could subsequently use that to stratify your reading strategies. Basically say, for example, we don't read 50% of our cases and then miss 5% of the cancers. Obviously, by increasing the recall rate on this side a little bit, we would easily compensate those 5%. There are many strategies out there that you could employ, particularly in double reading. Here they suggest things where you could reduce 70% of the workload and actually get the same amount of cancers, right? By just dismissing a whole bunch of negatives. This is the most famous trial in this aspect. They actually employed the treating system in a randomized controlled trial. One arm just had double reading, according to the standard European practice. The other arm had single reading in all cases ranked 1 to 9, right? Cases ranked 10, the most suspicious ones, were still double read. They actually also got the AI output, so they knew what things were suspicious. This would lead to a workload reduction of 44.3% and led to an increase in cancer detection of 20%. Quite recently, they presented the full study results. It's actually an increase of 30%. Treat a third of cancers at half the work. What more can you wish for? Doesn't work in America, right? Because you have a single reader practice. So here you can basically exploit, for example, the negative predictive value. If the AI system says you're very unlikely to have cancer, the chances of a radiologist missing a cancer are next to 0. You see that we also have this for MR for the moment. This is the performance of a radiologist. We are not quite there yet, right? But we are climbing in that area. In terms of risk prediction, what you get to see is models that actually evaluate negative, normal mammograms, outperform any model that looks at family history, lifestyle factors, hormonal factors, and so on. This is the most famous of it. It's called MIRAI. And what it does actually, it evaluates a normal mammogram point. It's here compared to Tyree-Cuzick in a whole bunch of different cohorts. Basically, you go down from the red dot and you go right from the blue dot, you get the operating point of Tyree-Cuzick, right, in all of these models. Means looking at the mammogram, if you have it, is way better than actually doing Tyree-Cuzick. You can obviously go on with this kind of models. This is what actually allows to put in multiple mammograms. So 2 years later, you put in the next mammo, and then you adjust the risk. You can actually also input the classic risk factors in that. That doesn't add much, but it does add a little, particularly for the very young women. You could also do risk prediction based upon the age of the breast. So first you predict the age of the breast, and then you actually look at the age of the woman and see whether her breast is as aged as she is. If not, if the breast is older, her risk is higher. And you can use this risk prediction to actually select subsets of patients to find, for example, interval cancers. Here, if we would stratify based upon density, we would find roughly 22% of all the interval cancers if we would submit 10% of our patients to MR. Right? If we would take the risk score of the AI, we would find roughly 35%. If we would combine those, we would find roughly half of the interval cancers by sending 10% of our patients to MR. So we can optimize our screening strategies. And you see that I think in the end, for the normal mammograms, the output of the mammography machine will be something like this, right? Reports the density, says there's no lesion, and then gives you the risk. So you can use that to stratify patients and select women for better screening techniques. In Sweden, they actually applied a study like that. They actually looked at mammography risk and sent a group of women to MR for supplemental screening. In that group of women, they found 64 per 1,000 additional cancers. We did a study in the Netherlands where we sent women with extremely dense breast to supplemental MR, right? Because we think density is a major issue. The groups were comparable. The proportion was the same. In dense, we found 16.5 per 1,000, right? So they found 4 times as more. By using an AI model, predicted the risk of cancer being present in that mammogram. I must admit, some of these cancers in retrospect were actually quite well visible. So maybe a cheaper option is just to reread the mammogram sometimes. Then finally, lesion classification. There are AI algorithms out there that tell you whether or not you need to put a needle in a lesion like this, right? Also here in MR tells you more or less there is an enhancing lesion, but this is so likely benign that you can obviate the biopsy. Roughly can reduce 40% of biopsies according to or compared to our current practice. You can go a little bit further with this. Here we combine mammography and ultrasound images into one combined risk model that does actually predict molecular subtype of breast cancers and actually separates them very nicely. It's very good in separating ER positive from ER negative cancers by just looking at the images. Not very useful here. You will have a biopsy, but maybe sub-Saharan Africa can actually make use of this kind of data, right? Because these images will be there. Eventually, you won't want to go beyond just predicting what type of tumor you're looking at and then look at therapy selection and response prediction. Cancers are not uniform and will therefore actually behave differently when you give chemo. You can use classic radiomics features to actually predict that, but you need to actually put the luminal or the molecular subtypes in, otherwise it doesn't work. Chemotherapy response predictions with CNNs have been performed, quite a few. Numbers are very, very small, 140 here. This is only triple negative, once again 140. And if you look at the studies that are out there, the biggest studies have roughly 500 cases in, right? Think of mammography, we're talking 1 million mammograms, right? Then the AI algorithms perform very, very well. This is child's play, to say the least. Nonetheless, we're getting there. This model actually incorporates mammo and MR and clinical factors into one multi-parametric model and then tries to predict the risk or the likelihood of PCR that achieves an area on the curve of 0.8. And then if you look at how important the factors are, the major factors are obviously the molecular subtype and therapy. That's what you use to actually select the therapy. But here are the imaging features, and they actually outperform things like the clinical stage or the clinical nodal stage. Right? You can actually take that even step further and predict an optimal regimen. This has not been published yet, but we are working in this direction. In this case, we actually inputted different regimens. So we had patients that had only single HER2 blockage, patients that had double HER2 blockage, or patients that had only AC, or patients that had AC plus a taxane, right? And then we tried to sort of predict what the optimal regimen would be for these patients. And you can see that these models, in essence, have the capability to say from some of the patients that were treated with heavier regimen, well, maybe they would also have the PCR with a lower regimen, right? And the other way around, they also say, okay, even with the high regimen, they will not achieve a PCR. Maybe these are the optimal study patients for subsequent studies. This is where we're heading with AI. We need much bigger data sets, and we need all of you to cooperate in that, otherwise it will not work. But I think there is a lot of very nice things coming from this. With this, remember, AI is everywhere. Memo is very good. In MR, we're just starting because the data sets are very, very small. On the Gartner hype cycle, I think detection mammography is really ready for implementation, right? Risk prediction is rapidly coming there. Response prediction is slowly going down because there's a lot of parameters that we need to put in. We need multi-parametric data sets to do that. And the AI specialists all think that we will solve that with foundational models that know normal. We'll see. It's not going as fast as you would hope for, but still going at an amazing speed. And I think eventually AI will be a major driver in our everyday lives. That's it. Thanks for your attention.
Thank you so much, Dr. Mann. Next, I'd like to welcome Erika Hamilton from Sarah Cannon Research Institute, who will be talking about drug discovery and applications of large data to improve care.
Thank you. Well, while we wait for the slides to load, hopefully they're loading, I will let you in on a secret that I'm actually not an AI expert at all. In fact, I don't think people would even classify that I'm good at technology. I'm just a medical oncologist, a breast medical oncologist, and a clinical trialist. But I said that I would do this talk. And then the more I thought about it, I thought, you know, maybe somebody like me is the perfect person to give this talk. Because I hope I leave you with the fact that AI is here today, and there's actually a lot of practical applications and things that you may already be doing in your clinic or could be doing. Okay, so here are my COI disclosures. All of these funds are for research, none goes personally to me. And this is gonna be my agenda. So first I'm gonna talk briefly about AI and novel drug discovery. So this is really the advantage of pharma and also ultimately to us who may wanna use these drugs. And then I'm gonna talk about deep learning for genomically led trial matching, ChatGPT applications for trial matching, and deep learning for models for treatment outcome prediction. I'm then going to move on to AI to optimize clinical trial delivery and execution, and I'm going to leave you with a provocative thought about machine learning to identify populations at risk for poor care and outcomes, and where we may be able to lead in with more resources to make oncology care more equitable. So if you're like me and you're not an expert in AI, here's some terminology. So artificial intelligence, machines' ability to perform functions that are usually thought of human intelligence behavior. Learning, reasoning, solving problems. Machine learning, a subfield of AI that really looks at algorithms and models to learn from data and make predictions or decisions. And deep learning is a subfield of machine learning uses neural networks with multiple layers that are especially well suited to handle large data sets. You can imagine GS data, for example. So my first example is generative AI. So you can see here that we're taking molecular information, protein structure, and info on biochemical interactions. We're training AI to learn from patterns in these data to predict potential drug candidates for pharma. Generative AI can digitally design a drug molecule, predict how that's going to fit in with a pocket that they're wanting to target, and then ultimately they're made in the lab. That's tested with interaction with the target protein. And the key is that then information of whether that worked or didn't is fed back into the model, so next time AI gets it right more often. So just said another way, it's essentially synchronized combination of hardware, software, and data to industrialize drug discovery, whether we're talking about genomics, proteomics, real-world patient data, or even transcriptomics like RNA. And so is this being used today? Absolutely. And in fact, several companies are pretty forthcoming on the fact that their drug was designed by AI. Recursion is an NF type 2 drug. It's an HDAC, and they did use AI-driven drug discovery to develop this for NF2 meningiomas. Relay also has an FGFR that was used, an AI platform to design. So let's move to deep learning a little bit. So as we've already talked a little bit about earlier, deep learning certainly can analyze images. It can also look through genomic data and predict outcomes and tailor treatments for our patients. It can also take multimodal data. So you can imagine an EMR with NGS data and kind of fuse that together, or also survival prediction for us as well. So I'm using an example here from Sarah Cannon. So in 2017, we acquired a company in Boston called Genospace, essentially a precision medicine platform. And what we do on the left is we get raw feeds of all of the NGS data from the major companies every night on all of our patients. So anything that's updated, anyone new that's seen and is now our patient, we're gonna get a raw feed at night for that. We pair that with our MR, so clinical data. What tumor type do they have? What setting are they in? What prior therapy have they already failed? And we can also look at EDCs. This all comes together, and then in the middle of the slide, we have data scientists. This gets transformed, and ultimately we can spit this out as genomics-driven precision oncology, emailing the physician saying, I see that you have a patient that would be eligible for this study with the right mutation. Have you considered this trial? Site feasibility and population analytics. If we have one site that has a very high preponderance of patients with maybe BRCA alterations, then that site would be a great site to have a trial of a PERP inhibitor, for example. And then also I'm going to talk a little bit more about EHR to EDC direct data transfer that we're entering right now. So this was an example that I have blinded from a pharma company that came to us and said, we're looking for a protein null phenotype, and we think we're gonna have to test 100 people to find 10 of these. And what Genospace did for us was come up with an NGS signature that would predict this phenotype based on mutations. It's not perfect, it's not IHC, so it can't do it every time, but we thought we would have to only test 10 to get 5. So we thought we were gonna increase our yield to getting 10% of patients that would ultimately go on to be able to get the drug up to 50% of patients. And this is pretty important because oncologists aren't patient. We get discouraged when we have to screen 100 patients to find 10. And so this is how it worked. We essentially got all the NGS tests. These were ordered standard of care. It wasn't specific for the study. It was information that we already had. And then that's all put into Genospace. We then can identify the patient that have loss of function mutations that we would predict to have IHC null, then go and tell that patient and their provider care team, essentially, I think this patient's very likely to be IHC null. We would test, we would confirm, and then ultimately, again, we go back and give the AI platform the information about whether it became true or not, so their algorithm is even better next time. And so this is what it turned out to be. It was a study that was supposed to take 5 years to find the patients, and we did it in 2 years. We went from a 10% boost that they initially thought that they were going to find, 1 in 10 patients having the null phenotype, to we actually ended up exceeding the estimate a little bit, and we had 60% enrichment. This is now a drug that's in phase 2, and essentially related to significant time and cost savings by reducing the number of screening activities and preferentially doing the testing on the patients that were most likely going to have the alteration. Okay, so ChatGPT, it doesn't just write emails or let college kids cheat on essays. So for clinical trial matching, I don't know if you're one of the people that reads a lot of companies' protocols, but I am, and they're 200 plus page PDFs that are not standardized across anything. Genospace clinical trial match tool uses just ChatGPT, and typically we have to have full 3 to 4 full-time people that essentially do protocol curation. They've got to go in and say, what line are we looking for? Who are we looking for this? And then essentially all inclusion and exclusion, and put this into Genospace so our clinical trial matching works. So the goal was to build a PDF chat box that we could essentially chat the PDF and explore the GPT's ability to query trial protocols, so this didn't have to be done by our staff. So this is what it looked like. We essentially had the PDF. We dumped it in, and we would ask it some questions. Eventually, we trained it. Please give us a diagram of what the design of the trial is. Please tell us what you're looking for. Please tell us what the inclusion/exclusion is, and it would spit that out. And now we're actually training it to then spit it out in the code that GenaSpace uses that we can put directly back into GenaSpace so our scientists don't have to do this. And this is what it looks like. So this is SCRI GenaSpace in the top left corner that you can see, and it will pull up. If I put in what my patient's mutation and their tumor type, it will suggest me studies that would be a good match for my patient. So definitely useful in the clinic, especially if you're seeing lots of different patients with lots of different alterations. So what about this? Leveraging data to predict treatment outcomes. So predictors for immune checkpoint sensitivity are imperfect. And I'm going to use an example that isn't breast cancer. Shocking, I know. But essentially, we looked at broad panel NGS and asked the question of could we identify patients that were more likely to respond to immunotherapy separate from TME, separate from PD-L1 status. And so you can see on the left, we had all of our NGS reports, and we paired that with the smaller gray circle of who had EHR records of having immunotherapy and how did they do on that? Did it work as well as we wanted it to? And you can see there's multiple tumor types over on the right that ultimately were added. This is what we saw. In colon cancer, mutations in a RID1A correlate to longer time to treatment failure, and P53 correlates to shorter time to treatment failure, irrespective of PD-L1 positivity. And in non-small cell lung cancer, LRP1B correlates to a longer treatment time to failure, and EGFR mutations correlate with shorter. And this has subsequently been validated in multiple labs. So essentially, the results from the commercial NGS panels could help us who is going to be the exceptional responder for immune checkpoint inhibitor. So what about optimizing clinical trial delivery? And this is something new we're using with our CRO at Sarah Cannon. So this is Accelero. And so from clinical development, from preclinical to post-approval, we can expect better placement of these trials among our sites, faster recruitment, and improved access. We can use our personalized medicine teams to find the right study for the right patient and even ping that individual provider and do the hard work for them of matching the patient to the trial. And then ultimately, even with data. So we have EHR to EDC transfer. That's also going to mean that companies are going to have real-time data, meaning if a patient walks in, we don't have to wait for our data coordinator 3 days later to put in the CBC to the EDC. When it hits our EMR and results in 20 minutes, that's going to automatically be in there for the company to see in real time. Really important for phase 1 trials where we don't want mistakes, and time is really of the essence of how quickly we move. So this is what it looks like. And I'll caution that we're not, the goal is not for Sarah Cannon to be the CRO for all studies. That's not what we want. The sponsor is still going to be the CRO. They're going to perform all their CRO function. What we're going to take with Accelero is for our sites within the Sarah Cannon US Oncology Network, we're going to do the site selection, the feasibility, and the oversight using AI. Which site is going to be good at this? We're going to be monitoring the data management and the biostatistics. And so essentially, it's going to be one EHR for us. And it's going to have automated EHR to EDC data transfer, and I'll get into this a little bit more. So what about site identification? So it's going to enable us to find the sites that have the patient population, that don't have competing trials, that the physician's interested, and also site capabilities. Is it a phase 1 unit? Does it have a refrigerated centrifuge? Can they do 6-hour PKs? And so really enable us to get better at building the right menu. My program manager is incredibly organized and has an Excel spreadsheet that we can't even print on large paper of every site we have and what trials they have in this little grid. We're not going to need to do that anymore. GenaSpace really can do that for us. And EHR to EDC, we're calling it 2E, direct data transfer. So this is going to end up being about 50 to 80% of patient data for treatment visits that can be populated automatically. So you can imagine vital signs, their weight, their labs that day, what the dose of the drug was given, was it signed off and given or was it not? All of that's going to be automatically pulled. Things like DLTs, things like how the patient's feeling, that is still going to all be subjective and ultimately is going to require manual data inputs. But if we can get rid of half of the work for our data coordinators, this is going to be a big deal. So ultimately, Accelero transforms trial design and delivery through execution to accelerate delivery, also through feasibility and site selection to make sure that the sites that are most likely to succeed on an individual trial has that trial, and also patient identification and central screening. So an oncologist that's busy in clinic isn't having to flip through a multi-page paper to try to figure out which is the right study for the patient that's in front of me. And finally, I'm going to leave you with this, AI to improve health equality. So this was a study, a development of a multi-level model to identify patients that are at risk for delay in starting their cancer treatment. And so some of this isn't going to surprise you. Patients are less likely to experience a delay if they're diagnosed at their treating institution and don't move locations, if this is their first cancer, if they're white, Asian, or Pacific Islander, if they have private insurance, and they don't have other comorbidities. But patients were more likely to experience delays in starting treatment if they came from disadvantaged neighborhoods, if they came from neighborhoods with higher Hispanic residents. And interestingly, this was not seen for neighborhoods with concentrations of Black residents. So really kind of asking the question of, can we predict who might have a bad outcome or who might have a delay before it happens, and then employ resources and programs to that area to ensure it doesn't. Ultimately, I think we all get better in terms of health equity and making sure that everyone has similar outcomes in cancer. So here are my conclusions. AI and big data are already being used in oncology to improve cancer care and research in many ways. One, it can help us with personalized treatment. AI can analyze patient data to identify unique patterns or markers that can be used to tailor treatment plans. So this is our clinical trial matching example. It can predict treatment outcomes, how individual cells will respond to drugs and the likelihood of treatment success. This was our example about generative AI. Big data integration. It can combine genetic, histopathology data, NGS data to improve clinical decision-making in the clinic. And this is an example of our checkpoint inhibitor response. We can also accelerate clinical trial delivery with Accelero. And finally, in terms of public health, AI can be used to monitor cancer cases and relate them to environmental, genetic, socioeconomic factors, and ultimately can identify those at risk for poor delivery or poor outcomes, and hopefully intervene and prevent that from happening. Thank you.
Thank you so much, Dr. Hamilton. So now we have some time for questions. If anyone wants to come to the microphone. We have some coming in online. I think one that's kind of relevant to all of your talks is there's a question about, on the context of the quality of the input data, whether you're talking about artifacts on pathology or imaging or just what's entered in incorrectly into the health records. How should models be designed to kind of approach those factors?
That's a good question. In our foundation AI model approach, we implemented two separate and independent methods to address the question of image quality. One is about image normalization. That is, for any input image, we normalize it to the regular distributions that we have observed in the training data. And the other strategy is about image augmentation. That is, in our training process, we also artificially, synthetically generate additional images based on the observed images to simulate what may happen in the real world. And that's our strategies in dealing with pathology imaging qualities.
Yeah, we do sort of the same things, but I also think that we need to focus a little bit on uncertainty modeling, in the sense that you sometimes get an AI output on, let's say, a brain scan that was entered as a mammogram, that there might be a breast cancer somewhere, right? We need to get our AI algorithms in such a way robust that they actually notice that an image does not fit the actual standards and then does not provide an answer rather than a completely absurd answer. These kind of things are currently not well taken care of in most of the algorithms that are out there, and sometimes that really erodes the trust in an algorithm. So we really need to take care that we actually take these kind of measures.
Yeah, I guess from my standpoint, maybe a couple different types of answers to this. So, GeneSpace, for example, our clinical trial matching, it's not perfect. Every time that they give me 5 trials, the patient may not be eligible for one of them, but it still curates it down to much, much smaller than we otherwise would have to flip through. And then I think as we're able to rely on machines to do the easy things that are brainless, right? Translate a CBC. I mean, that's essentially what data and monitors are for, is for QC, because there are transcription errors. How many times do we get, a query of the hemoglobin was 93? No, it was 9.3, right? And so some of this is going to actually be mistakes eliminated when we use direct EHR to EDC.
Great, thank you.
Hi, Dan Hayes, University of Michigan. This was a great session. And to be a little snotty to start with, it's nice to see it go from good ideas, lots of chaos, and what I call stamp collecting to actually implementing these things into something useful clinically. And the three of you kind of went that way. I congratulate you for that. Dr. Hamilton, have you, with all the stuff you've shown here, which blew me away, frankly, have you run into bureaucratic and privacy issues in regards to HIPAA and that sort of things, screening all your patients' genomics to be eligible for a trial? Have those raised any concerns or red flags?
It hasn't. We acquired the Genospace platform in 2017, so that is all internal to us. I mean, it's very similar to your EMR, where we have to have, a username and password sign-on, very similar to an EMR. And again, it all happens internally, so we're not kind of, shipping this data or having to rely on fax machines or any of that. So we haven't had issues. I mean, I think the challenges have been maybe more on the human side, right? Willingness for people to receive an email suggesting maybe what their patient should do and not be offended by that. Talking to pharma companies saying, we're going to kind of pick our sites and you're not going to do that. That can be a challenge, right? But I think this is where we're heading, because the reality is there's so much data out there and humans can't process it all. We can't do it effectively. We make mistakes, right?
And since you wholly own Genospace, is this available for licensing to other sites, or this is totally yours?
No, we're using it completely within our network.
Too bad.
Put a proposal together.
Hi, Dave Mankoff from University of Pennsylvania. Had a question for Dr. Mann. I wouldn't agree with Dan. This was a spectacular session. To go to the discovery part of the title, and Dr. Mann, you got to this towards the end of your talk, is as you begin to identify features from the images that will predict outcomes in response to therapy, is this an opportunity for discovery? This is the rare time when you get all those genes and functions to have to come together in a macroscopic structural or functional image. And have you thought about how AI might not only be a way to get the diagnosis, but actually discover factors that hadn't been identified before?
This is for you, I think.
Yeah, that's a great question. So for our analysis, we also aim at building models to enhance discovery. And to your point, first we build this model to identify any potential signals in the pathology images related to any important outcomes of interest. And we may not really know where the signals may be coming from. So this will be a completely data-driven exploratory analysis. And as we've seen in our current results, because this is purely not strongly supervised, it's a weakly supervised approach, allowing the model to explore the data and identify any useful information. So occasionally we are encountering scenarios where the model focuses on certain patterns that is really hard to interpret. And to accommodate this, currently we are building a multi-modality model, first learned from the pathology textbooks and other literature to identify the basic concepts in pathology. And currently our preliminary results shows that this approach would be able to better link existing concepts with these newly discovered features that may be helpful for enhancing future discoveries.
And I was almost really directing it more at the imaging talk, where you integrate across features that you don't otherwise have and relate those to microscopy, which seems an area that's quite ripe for discovery.
I think there's a lot to be done, and if you look at the current methods that are used to actually figure out where the signal comes from in images, they are honestly still quite coarse, right? So if you see a heat map of GradChem or an occlusion analysis, then there are red dots that actually signal the features in the images that are most important. But at this point, I would say that it is not really at a level where you can really say, okay, this is going to be my next target. Even though what I find really striking is that many AI algorithms that we have here actually find much more discriminating features outside of the tumors than in the tumors themselves, right? So actually, it really shows that the stroma and the part around the tumor, the habitat of the tumor more so to speak, is a very important driver for tumor aggression and response.
Thank you. Very, very interesting session. Appreciate it.
All right, with that, I would like to thank the speakers for their talks and thank you all for your attention.